Today we're going to look at this example. It's a linear quadratic tracking problem for finite time case. The problem is stated here. The plant is given in this time-varying differential equation. X dot is equal to ax plus bu. So y is equal to c times x. Y is called output. The E is defined as the difference between zt and yt. So zt represents your desired output, but yt is your actual output, and you want to minimize the difference between the two. The performance index is in the standard form, which includes the terminal cost and also the cost along the path, which is in the integration form from T0 to Tf, E transpose Q times E plus U transpose R times U. And boundary conditions include the initial condition x0 and the final state is free. We followed the Quadratic's minimum principle procedure and we got this result. And to put the conclusion that we got into a procedure to find out the optimal control, the first step is to solve this matrix differential Ricardo equation. It's in this form. It's different from the Ricardo equation for the linear quadratic regulation problem, because here we have a C matrix and the output is different from that, and also the error is defined as z minus y. So solve this differential equation that will give us P, and P is a matrix. One boundary condition is at a Tf, P Tf is equal to C transpose times F times C. In addition to that, another differential equation you solve is GT, and this is given in this form. And if we can find a GT, then we will be able to put the control together. The optimal control is given as negative R inverse B transpose times P times X plus R inverse times B transpose times G. So if we have a G and a P, we will know the optimal control. And also remember, optimal control depends on the optimal state X, which requires us to find an X first. So we come back to step 2, we need to find an X. So the way to find an X is to submit this U function into the differential equation that will give us this form. So we solve this differential equation, we'll be able to find an X. Then we plug X in there, I find optimal control U. So that's how we solve the problem. And the optimal cost is also given in this form, half X transpose times P times X minus X times G at the initial condition plus H at the initial condition T0, where this HT is a solution of this differential equation. And we know the terminal condition H at the time Tf, so we can find a H at the time T0. After we find a H at the time T0, we'll be able to find the performance index. Let's look at this example. We have a second order plant. x1 dot is equal to x2, x2 dot is equal to negative 2 x1 minus 3 x2 plus u. The output is equal to the states, which give us C matrix is equal to identity matrix. And the performance index is given in this form, and from this performance index, we'll be able to find what is the terminal cost F at a Tf is equal to this. And the Tf is given 20 seconds. And matrix Q is related to the states, which is from here. And remember, we do not have half there. If we put a half here, and this will be multiplied by 2. So that's why the Q matrix is 2, 0, 0, 0. And a ZT, we can find it from here. So ZT is equal to 1, and the second one is 0. And R is equal to 0.004, which is 2 times of this because we need to put a half in front of this integration. These are the basic information we have. So looking at the procedure, the first step is to solve the differential Ricardo equation and also the other differential equation for G. So that's what we did here. We define a few matrices. One is E, the other is V. So this is the P dot. So this is from a previous code. I didn't update this session. Minus A transpose times P plus B times P times. So this is represented by the matrix E times P minus VT. And we defined the V over there already. We define these variables, and the final condition we already know. And then the first step is to solve the matrix of differential Ricardo equation, because we're going to solve P and G at the same time, so you can solve them together. So I put a P and G together, and here the matrix of P is composed of the first of 4, because the P matrix is of 2 by 2. The first of 4 elements, so here n is equal to 2. We have 2 states, n is equal to 2, and m is equal to the number of the control. So we can get this from the size of B. The number of rows, the number of states, the number of columns is equal to the number of controls. We define P and G is the rest of 2. Then we define E, V, W. Then we'll write the differential equation. The different dP or dt is equal to negative P times A minus A transpose times P plus B, P times E times P minus V. So this is the first differential Ricardo equation. And the G equation, G dot is equal to negative A minus E times P transpose times G minus W times ZTF. ZTF is Z evaluated at time TF. We collect all this information, then we define the differential equation. Toward the end, we need to put them in one column. And that's all limited by the ODE solver. It can only solve the differential equation in one column, so it cannot solve the matrix directly. But it's not a big deal. We can put a matrix into vector form. Then we put them back after we solve it. So this is how we solve the P and G matrix. The second step is to solve for the optimal states. We'll put the optimal state in XX, and the initial condition, which is the first element, is equal to X0 transpose. And the dx dt that is given. I just used the Euler method for integration, because from the previous step I used ODE 45 to solve P and G. So I use the same time t to calculate this integration. And then I will find the optimal states. After you find the optimal states, next step is to find the optimal control. And optimal control is equal to negative k times x plus R inverse times B transpose times G. So this is how we find the optimal control. So optimal control is called UU, the optimal state is XX. Then we have everything. The rest of few lines is just the plots. Let's take a look at the results. So we run the code, and it will give us some plots. So here are plotted the states. So you can see like how x1 and x2 changes. So this is a problem. We want x1 to be converged at 1, and x2 we do not really care, but we set it at 0. The optimal control is the second plot over here, and this is the control that you supply to the system, then it will give you this response. And you might wonder what happened here. Remember, we solved the problem backward. The final condition is given. We solve it backwards to get P from T0 to TF. Because we solve it backwards, and eventually P will convert to its steady state value. This is what happens to matrix P. Because the P matrix has 4 elements. P11 is the first element, P12 is the first row, second column, and P21 is the second row, first column, and then P22 is the last element. And similarly in G, you can see for a long time from 0 to 19 seconds, it's a constant until the end. So this is a control. So toward the end, because both P and G changed, this control also changed. What happens if I change the terminal time to 5 seconds? So initially I'll give it 20 seconds. It looks like the system can be controlled within a much shorter time, say like 5 seconds. Up to here, I should be able to see the system being stabilized already. So this is our control, this is states, and you can see that by 5 seconds the system already get there. Let's see what happens if I change the final time to 5 seconds. This is GT. So similarly, toward the end, it will deviate from a constant number. This is the matrix P, and this is our control, and this is the states.